new results on field spectroscopy data in the Alps for studying snow and ice variability, and is a collective work from myself from CNR, the Institute of Polar Sciences, colleagues from the University of Milano Bicocca, and colleagues from the Environmental Protection Agency of the Valle d'Aosta, and a colleague from Telespazio and a company called JP also. This is the outline of my presentation. I will start with the motivation of studying snow and ice and the cryosphere in general from remote sensing data. Cryosphere is an important component of the Earth system, and snow can seasonally cover up to 30% of land surface, so it is important for freshwater availability and for ecosystem and society as well. Also, glacier ice is important to study from a remote sensing perspective because it provides fresh water at mid-latitudes. I'm not mentioning the effect from polar ice sheets to the control of sea level rise. In any case, cryosphere variability is related to climate change and to the change of atmospheric temperature and solid precipitation, both at mid-latitudes and the poles. So let's look in details the optical properties of snow and ice. We can see the spectral reflectance of snow is decreasing as the snow ages. So we can estimate the state of the surface layer of snow and ice, for example, trying to exploit this absorption feature in the spectrum. This absorption feature are related to the refractive index of snow and ice, which features again particular absorptions that can be exploited also to decouple dry snow from wet snow from hyperspectral data, both from satellite and field and from field spectroscopy. So which snow and ice parameters can be retrieved from hyperspectral data? Main parameters are snow and ice albedo, which give us an overview of the radiative balance of the surface, but also some structural parameters related to the grain size, and also the specific surface area can be derived from the grain size as well. As I mentioned, the liquid water content of surface snow and ice can be retrieved exploiting absorption features in the near infrared. And also one aspect is related to the impurity concentration. So their impact on the radiative properties of snow can be derived from this variable. So the radiative forcing, that is basically the amount of radiation that is trapped on the surface snow and ice because of the presence of these atmospheric impurities. Now I'm going to present a couple of sites that we are working on the last years. One is Plateau Rosat, is located at 3,400 meters above sea level beyond the Swiss border in the Monte Rosa Massif. And the other one is Tornion, is located at 2,000 meters above sea level and is run by the colleagues in Aosta Environmental Protection Agency of Valle d'Aosta region. This site, Tornion, is an experimental site with a lot of instruments for studying both vegetation phenology, but also snow dynamics. This ice is a meadow, so it's seasonally covered by snow from October to May. And there are several instruments for, as I said, for studying surface radiation, webcam, sensor for snow depth, snow water equivalent, and snow surface temperature. In this presentation, I will focus on the snow reflectance instrument, the spectrometer that we installed in 2017 at the site that covers the 400-900 nanometers spectral range. And we are using this spectrometer for analyzing the seasonal changes of snow cover and also for calibration and validation of Prisma data. Okay, the other site is Plateau Rosat. We don't have an unattended instrument there, but we occasionally go there for acquiring field spectroscopy measurements. This is a good playground for field spectroscopy because it's a rather flat area and it's quite easy to reach both during winter and summer season because it's a glacier, so it's covered by snow or ice for all year. We've been focusing on some retrieval scheme of snow parameters using data collected in Tornione and Plateau Rosà. On the left side, you see some 3 examples of snow reflectance or plain albedo, as is represented here. And in red, we have the optical data collected from the automatic spectrometer, and in black, dotted black, there is a model developed by our colleague Alexander Kokhanovsky, and this model is able to estimate a series of parameters related to the snow optical properties, and parameters are again snow grain effective radius, the dust concentration and size distribution, the broadband albedo. And regarding the instantaneous radiative forcing, we developed a novel scheme for estimating this parameter using the Sneaker model. We basically try to understand if, looking only on this small spectral range covered by the automatic spectrometer, we are able to estimate both the grain size and the instantaneous radiative forcing from this data in a continuous fashion, since the spectrometer acquires each day, each 5 minutes, measurements of snow reflectance. Some preliminary results from a comparison between the spectrometer and Sentinel-2 data are related to the albedo from 2017 and 2021, and also for snow effective radius. I want to mention that at some point we changed the 4 optics of the instrument. So for the first 3 years, we have the hemispherical reflectance factor, and for the last year, 2021, we have the hemispherical conical reflectance factor. So now we are trying to understand how the retrieved parameter change as a function of the 4 optics, because we changed for a direct comparison with Prisma hyperspectral satellite data in this case. This brings to the Prisma section of the presentation. We used 2 acquisitions, one acquisition in Tornione and one acquisition in Plateau Rosà. As I said, in Tornione we have also the automatic spectrometer, and in Plateau Rosà we don't have. So we only made use of field spectroscopy acquired manually in the 2 sites actually. So for this calibration and validation activity, we have 2 methodological approach for the radiance. We propagate the surface radiance collected in the field using atmospheric parameter to the top of atmosphere. So using a radiative transfer equation. In this way, we are able to directly compare top of atmosphere radiance measured by Prisma and that measured in the field and then propagated at the top of the atmosphere. Instead, for reflectance, okay, this is reflectance, not radiance. For reflectance comparison, we directly compares Prisma level to the surface reflectance with the reflectance measured in the field. So some results from the 2 sites in Tornione. There is a good agreement for level 1 top of atmosphere radiance. Here you can see the spectral evolution, the field spectrometer in black. In red, the Prisma acquisition at the top of the atmosphere. In light blue, the rocks acquisition, and in blue points are the Sentinel-2. So in general, there's a good agreement between those different sources of data, and the mean absolute difference error is below 5% for most of the spectral range of interest. Regarding Plateau Rosà, we show here only the comparison between the spectral evolution, so the field spectrometer, Prisma, and Sentinel-2. And again, we have a very good comparison between these 3 actually sources of data. We have some error at the beginning of the spectrum below 500 nanometer, and this could be to atmospheric scattering or the effect of the impurities contained in snow. The comparison regarding reflectance, we present only for Plateau Rosà, the comparison between spectral evolution, Prisma, and Sentinel-2, because we had some problems with Tornione site. We had some saturation on that area during the acquisition. So we are presenting only this comparison, which is again quite good, even if we see a slight overestimate of reflectance from Sentinel-2. So this brings me to the conclusion of my short presentation. We presented two experimental sites that we are employing for investigating Prisma performance on snow and ice covered areas, and two field campaign where we collected field spectroscopy measurements and compared it with the contemporary Prisma acquisition in the Western Alps. Those data from the automatic spectrometer represent a novel source of information for systematic and continuous measurements for calibration and validation and temporal monitoring of snow melting dynamics, because with this parameter that I presented, we are able to describe and also compare with the snow dynamical model surface parameters such as albedo, impurities, and grain size, which are quite important for assessing the impact of atmospheric temperature, for example, to snow melting. And also the preliminary comparison with Sentinel-2 is promising, as I showed. Prisma level 1 and level 2D spectra show again a good agreement with field measurements and Sentinel-2 data with the error lower than 5%. We have now to deal with this problem of saturated pixel for fresh snow and large solar zenith angle acquisition. So when we have the sun not very high in the sky, let's say, we have problem of forward scattering in our field side, and we are trying to understand how the topography of the field influence this kind of problems. So to conclude, Prisma data look promising for studying the cryosphere, and it's a novel application. There have been several studies using Abiris in the United Southwest US, and also some recent work from Greenland. So with this Prisma data, we are able to study snow and ice dynamics and surface properties at global scale with an unprecedented accuracy. So I want to acknowledge the project that made possible to produce this presentation. All are funded by the Italian Space Agency, and I want to thank also the ARPA Valle d'Aosta for maintaining and running the experimental site in Tornion. Thanks for the attention, and I'm open to questions.